Engine timing is the agreement between piston position, valve movement, and fuel injection. When that agreement is correct, the cylinder fills, seals, fires, and clears at exactly the right part of the cycle. When it is wrong, even a mechanically healthy engine can become a hard-starting, smoking, low-power machine, or suffer piston-to-valve damage. In this lesson, we will physically follow the crankshaft and camshaft through all 720 crank degrees of a 4-stroke diesel cycle. Then we will connect that movement to mechanical inline pumps, rotary distributor pumps, unit pump systems, and modern common rail. The most important rule is simple. Never time an engine from a guessed mark. Identify the correct cylinder, the correct top dead center, and the exact OEM procedure. Technicians often say 1 revolution when they actually mean 1 complete engine cycle. Those are not the same thing. 1 crankshaft revolution is 360 degrees. A complete 4-stroke cycle needs 2 crankshaft revolutions, or 720 degrees. During those 2 crank turns, the camshaft turns once. Put another way, for every 1 crankshaft turn, the camshaft turns only half a turn. That 2-to-1 relationship is created by the timing gears, chain sprockets, or belt pulleys. The crank gear normally has half the effective tooth count of the cam gear. If the crank rotates at 1800 revolutions per minute, the cam rotates at 900. Every valve lobe therefore acts once during each complete 4-stroke cycle. Look closely at the timing drive. The crankshaft gear is the master because piston position begins at the crank. The larger cam gear follows at half speed. Timing marks establish their phase, not merely their speed. Correct ratio with the wrong tooth alignment is still wrong timing. At 0 degrees, number 1 piston may be at top dead center. But the marks must also place the cam lobes in the correct position. The drive may include idler gears, a chain tensioner, guides, or a belt tensioner. Idlers can change direction and transfer motion without changing the required final 2-to-1 ratio. Backlash, a loose key, a shifted reluctor, chain stretch, or 1 incorrect tooth changes when the valves and injection events occur relative to the piston. Now map the complete cycle on crank angle. We will start at top dead center between exhaust and intake, called overlap TDC. From 0 to 180 degrees, the piston travels down on intake. From 180 to 360, it travels up on compression. Near compression TDC, fuel is injected and combustion begins after a short ignition delay. From 360 to 540 degrees, expanding gases drive the piston down on the power stroke. From 540 to 720, the piston rises on exhaust and returns to overlap TDC. The piston reaches top dead center twice and bottom dead center twice, but the camshaft position tells us which TDC and BDC event we are looking at. During the first crankshaft revolution, the engine completes intake and compression. At the beginning, the intake valve is already opening or open while the piston moves down. Air enters because cylinder volume increases and manifold pressure drives flow through the intake port. The intake valve does not necessarily close exactly at bottom dead center. It often remains open after BDC so the moving air column can continue filling the cylinder. Once the intake valve closes, both valves remain seated and the piston compresses the trapped air. Temperature and pressure rise sharply. Near the end of compression, the injector starts delivering fuel before top dead center on many diesel engines. The exact angle is engine-specific. Injection start, ignition start, and peak cylinder pressure are 3 different moments. The second crankshaft revolution contains power and exhaust. Combustion begins around compression TDC, and cylinder pressure pushes the piston down. Both valves remain closed through the useful early part of expansion so pressure can produce crankshaft torque. Before the piston reaches bottom dead center, the exhaust valve normally starts opening. This blowdown event releases high cylinder pressure into the exhaust manifold before the piston rises. The piston then moves upward and clears the remaining gas. Near the end of exhaust, the intake valve may begin opening before the exhaust valve is fully closed. The crankshaft has now completed its second turn and the camshaft its first. Every piston stroke is finished, but only one of those 4 strokes produced useful positive torque. Real valve timing leads and lags the ideal 180-degree boxes. Intake opening can begin before top dead center. Intake closing can occur after bottom dead center. Exhaust opening can begin before bottom dead center, and exhaust closing can extend after top dead center. Around exhaust TDC, both valves can be slightly open. That is valve overlap. It helps scavenging and cylinder filling when the port, turbocharger, and cam profile are designed for it. It is not a universal fixed angle. High speed, low speed, and emissions-focused engines use different timing. Some engines also use variable valve actuation. For workshop diagnosis, never copy degrees from another engine. Use the exact timing chart, specified checking clearance, and measuring method for that serial number and rating. Top dead center by itself is not enough. Number 1 piston reaches TDC once at the end of compression and again at the end of exhaust. At compression TDC, both valves are closed and the cylinder is ready to fire. At overlap TDC, the exhaust valve is finishing and the intake valve is beginning. This is why a crank mark can align while the engine is still 1 full crank revolution out of phase. Confirm compression TDC with valve position, rocker clearance, pushrod freedom, or the OEM timing pin procedure. In a multi-cylinder engine, the cam lobes and injection pump elements then follow the firing order across the full 720 degrees. Do not assume a firing order from cylinder count alone. Verify the engine data plate and manual. A traditional inline diesel injection pump is synchronized mechanically with the engine. Its drive normally runs at camshaft speed on a 4-stroke engine. 1 pump cam revolution for every 2 crankshaft revolutions. Each cylinder has a pumping element. As the pump cam lifts a plunger, fuel first escapes through a spill port. When the plunger closes that port, trapped fuel pressure rises. A delivery valve opens, a pressure wave travels through the high-pressure line, and the injector nozzle opens only after its opening pressure is exceeded. Therefore, pump start of delivery, start of injection at the nozzle, and start of combustion do not occur at exactly the same crank angle. Static timing may be set by gear teeth, timing marks, coupling position, shims, or pump body rotation depending on design. A rotary distributor pump uses 1 pumping and distribution assembly to send successive high-pressure deliveries to the cylinders. The pump shaft remains synchronized with engine position, while an internal mechanical or electronic timing device can advance delivery as speed and load change. A unit pump or unit injector system works differently. An engine cam lobe provides the pressurizing stroke directly through a roller follower. With the spill or solenoid valve open, pressure cannot build for injection. When the control valve closes during the plunger stroke, pressure rises and injection begins. Reopening it ends delivery. The cam establishes the available pressure window, while the control valve defines the effective injection event. Correct cam phase, follower condition, injector adjustment, and electronic command are therefore all part of timing diagnosis. Common rail separates pressure generation from cylinder injection timing. The high-pressure pump fills an accumulator rail and maintains commanded pressure. It is not normally timing 1 delivery line to each cylinder as an old inline pump does. The ECU reads a high-resolution crankshaft sensor for speed and crank angle, and a camshaft sensor to identify engine phase and cylinder. Using load, temperature, boost, rail pressure, and calibration maps, it commands each injector at the required crank angle. It may schedule a small pilot injection to soften combustion noise, a main injection for torque, and post-injection for emissions control. The pump can still require correct mechanical installation on some designs, but injector timing is fundamentally commanded by crank and cam synchronization and ECU control. Injection timing changes combustion phasing. If injection is too advanced, too much fuel may begin burning early. The engine can develop a sharp diesel knock, excessive peak cylinder pressure, increased mechanical stress, and higher nitrogen oxide formation. If injection is too retarded, combustion continues too late into the expansion stroke. The engine may crank for longer, produce white smoke when cold, feel lazy, use more fuel, and run with elevated exhaust temperature. Camshaft timing error is even more serious because it changes breathing and effective compression. One tooth out can create hard starting, intake or exhaust blowback, poor power, and smoke. On an interference engine, enough phase error can allow the piston to strike a valve. Timing symptoms must be measured, not guessed from smoke alone. Timing can be lost through a sheared key, loose gear, incorrect idler installation, chain stretch, failed tensioner, belt tooth damage, worn pump drive, shifted reluctor ring, or incorrect sensor air gap. Read the evidence. Repeated witness marks, polished gear faces, and rubber debris point toward a drive problem. Equal low compression can suggest cam phase error. One low cylinder may be a local sealing fault. On mechanical systems, verify start of delivery or plunger lift with the exact dial indicator procedure. On electronic engines, check crank cam synchronization status and compare both sensor waveforms. A good-looking timing mark does not prove the reluctor or key has not moved. Before replacing an injector pump or ECU, prove mechanical phase, fuel pressure, electrical supply, and signal integrity. Use a controlled timing procedure. Isolate the machine, prevent accidental starting, and remove covers only after stored energy is controlled. Rotate the engine in its normal direction using the approved turning tool. Find number 1 compression TDC and verify both valves are closed. Install the correct timing pins or align the exact OEM marks. Confirm gear tooth engagement, backlash, chain or belt tension, key and dowel condition, and torque every fastener to specification. Set mechanical pump lift or start of delivery with the specified gauge and direction of approach. Remove every locking pin before cranking. Rotate the engine slowly by hand through at least 2 complete crankshaft revolutions and recheck the marks. Finally, verify valve clearance, sensor synchronization, fuel pressure, leaks, and start quality. Timing is a system. Crank, cam, valves, and injection must all agree.